1, Mississippi 2, Mississippi 3, Mississippi 4, Mississippi 5, 5, 5, Mississippi. Okay, we're in Unit 6, looking at practice problems. This is number 9.2. And in 9.2, we're looking at scenarios where we have ideal masses on ideal pulleys, and they're actually like an Atwood system. So what we have here is, we have a pulley up top, and then coming down from the pulley on each side are two masses, well, one mass on each side, but we've got two masses here, okay? Our first block has a mass of 14.3 kilograms, and our second block has a weight of 98 newtons. So be careful here. This weight here is 98 newtons, and remember, weight equals mass times gravity. So that's a little thing that they don't give us the mass here, they give us a weight. We could get the weight over here by saying that the weight it has would be 14.3 times gravity, and that would give us the value of the weight. So you know what, let's just calculate that real quick. 14.3 times 9.8 gives us 140 newtons. Okay, so that's the weight on this side. What we'd like to do is determine the magnitude of both of the blocks' accelerations, because they're moving together. And then what is the magnitude of the tension in the string? Because while these blocks are each trying to pull down, we have to imagine that there is a tension pulling up on each of them. That tension's like equal and opposite. So what's going on here? Well, we know that our left block here is pulling down with a greater amount of force, a greater weight than the right block. So we know that this block on the left here wants to go down, and the right block wants to go up. And that means our rope's kind of going to go around the pulley like this, right? So what we'll do is the following. I know that this direction of motion will be positive. So if, things that are going in the direction of motion will be positive. And if I take a look at that for the blocks then that means on my left side, going down will be positive and going up will be negative, because the direction of motion here is down. This block is falling. On the right side, we're going to call up positive and down negative. Now, if you've been following along with all these videos, did we just change the direction of positive? On the left side it's up, and on the right up is negative, and on the right side up is positive. Like, did we just change it? No. Because when I'm going up here, I'm going positive, and then I loop around the pulley, and when I go down, I'm still going positive. Okay, so we actually didn't change anything. We kept everything in line. That's how the directions should look there for positive and negatives. So at this point, what we can do is we can take a look at these objects, start trying to figure out what's going on with them in terms of their acceleration and tensions. If we want to look at the accelerations, sometimes it's easier, and in this case it will be because we know the weights, to look at everything as one large system. And if we do this, what we'll find here is that the sum of the forces will equal the mass total of the system multiplied by the acceleration of the system here. And if we look at all of our forces we have, well, let's just redraw this in a force diagram. We've got a weight and a tension on our left, and on the right we've got a weight and a tension as well. So if we wrote out our forces here in our F equals ma, starting with the left side where the weight is positive and the tension is negative, we're going to have weight plus negative, so minus tension, plus, and then on the right here our tension is positive and the weight is negative, so we'll call this weight left minus tension, plus tension minus weight right. And this is going to equal to the total mass multiplied by the acceleration of the system. We see our tensions are going to go away because they're the same, but our weights are going to be different. Our weights were 140 for the left minus 98 for the right. And now we have to figure out what is the mass total here. Well, I know the mass on the left. It was 14.3. But what's the mass on the right? Well, I could figure it out using my weight equation. I can say that 98 newtons equals the mass times 9.8, and if you do some quick division there, the 9.8 on each side, we quickly see that the mass here is 10 kilograms. So my total mass is 10 kilograms plus the 14.3, which gives me 24.3 kilograms. And if I want to solve for the acceleration here, I just need to work out this math, which is pretty straightforward. 140 minus 98 is going to give me 42. that's going to equal 24.3 times the acceleration. And then when I divide by the 24.3 on each side, I find my acceleration, which 42 divided by 24.3 is 1.73 meters per second squared. Okay, so that's our acceleration of both of the blocks. And that's a positive acceleration. We found that to be positive because, this block on the left is moving down, which is the positive direction. So that makes sense. If we want to get the magnitude of the tension of the string, we just need to go back and use one of our F equals ma equations that has a tension in it. We can either use the left one or the right one. Let's use the right one because the tension's already positive. It really doesn't matter what we choose here, but this tension's positive. So when we write out our F equals ma, here's the sum of the forces equals ma. This will be tension minus the weight equals the mass times the acceleration. And in this case, we know most of this already. We're looking for the tension, but we know the weight here is 98 newtons due to just the right block. And we know the right block's mass is 10, and we know its acceleration is 1.73 meters per second squared. So at this point, we just solve for t. 10 times 1.73 is going to be 17.3. We add 98 to each side to get rid of that 98. That'll solve us for the tension. So 98 plus 17.3 gives us a tension here of 115 newtons. And I rounded a little bit, but that's what we get. So we just took that value and put it back in, just like we did in many, many other problems, except in this problem, everything is kind of moving in a vertical direction here. So I just kind of took my U method of, what's the direction of motion? Let's make that positive for everything. And I set that up, looking at positive and negative and positive. Those are the directions of motion going around here. And in doing that, we were able to set up a system for F equals ma to get our acceleration, use that acceleration back to solve for a tension. And if I wanted to, I could have written out each of these free body diagrams, F equals ma equations, and then done a substitution method, but listing them all in one system is much faster if I'm looking for an acceleration there, and it saves us a little bit of time and headache. Okay, but in the end, we had to go back and write out this F equals ma equation anyways. So that's another connected objects problem, just for both moving vertically. That's called an Atwood's machine there. Not too bad, very similar to what we've done previously for a lot of our connected objects. You just need to make sure your positive and negative directions are correct, or else things are going to start going sideways on you. Okay? But for now, this is finished. Adios, take it easy. Be sure to check out some more videos when we start talking about friction and spring forces with Hooke's law. Adios, bye.